All right, guys, we'll get started now. So let us review what we did the last time. Python intro. We have intro to Python. So we talked about the fact that storage units are called variables in Python. Python is a dynamically type language. It means that you can put different things into the same box. A variable could be one moment containing an integer, another moment containing a string, and so on and so forth. It is something to watch out for. And that brings us to the notion of type hinting that I'll introduce today. And you may have seen it in my code. Then we talked about the fact that you doing conditionals in Python typically is if something is true, you do this. And when you look at this, you see that in Python, indentation matters. You don't have curly braces and things that you find in C, C++, Java. You don't see the statements end with semicolon. So there are no syntactic hints. The indentation is the syntax, part of the syntax. So what it means is that if you just, and this is the danger, and people find quite annoying when they come from other languages to Python. If they just so much as reformat their file, the code becomes completely different and it will behave differently. You need to get used to it. Once you get used to it, you may hate it, you may like it. Some people like it. They say the code is much neater, less verbose, less clutter. Some people hate it. They say that it shouldn't be so brittle that if you reformat the file, the code should just behave differently. But for better or for worse, it's a fact in the Python world. How does iteration look like? Loops. I said that we are going to do more powerful loops, but we did the while loop. While is you start out with some condition. While that condition is still true, you can keep doing things. And the hope is that you will gradually make that condition false. Otherwise, you'll be in an infinite loop. The other feature of Python is that you can do multi-line strings as you can. Right? So these were the things we did the last time. What we are going to do now is we are going to add more to this. So let me create a section here and call it session 2. September 19th. September 19th, 2020. So today, what we'll learn is more ways of doing iteration, looping. So in how many ways can we do looping? It turns out quite a few ways. And we'll learn quite a few of those ways. We'll learn about the for loop, which is something you may be familiar from many languages. So just to give you an idea, suppose you want to print something 20 times or 10 times. You would write in a typical language like C, C++, Java, if you're familiar with, you would say int I is equal to 0, I less than 10, I plus plus. Does this make sense, guys? Does this look familiar to you? I'm sorry. Right.
Yes.
Right. So you do. You have. Hang on, guys. I need to be able to see it. Do something. This is your typical. This is. Let me just call it the classic for loop. The classic for loop in C, C++, Java. Now, how does it, and I'll just comment it out just to, because this in Python would not be a valid syntax. But before I do that, observe that you start with 0 and the endpoint is not inclusive. In most computer science programming language, the rule is the left inclusive, right exclusive. You include the 0, but you exclude the 10. It's a right inclusive, left exclusive, left inclusive, right exclusive rule. Let me just call it a basic mnemonic. Left inclusive, right exclusive. Right. So in other words, mathematicians also write it as, those of you who are familiar with mathematical notation, they will say A, comma, B means start at A but N just before B. Do not include B. Are we together? This is the meaning of that. Actually, let me do one thing. Let me mark all of this as not the classic loop for Java. And we'll do something better. We'll indent it. Oh, sorry. And when we do that, hopefully it will, yeah. So this is our node, the classic loop. So how do we do it in Python? It's a good question to ask. In Python, we do it slightly differently. We would say for I in range, right? And you don't have to tell 0. You could say 0, but if you don't give 0, 0 is implied. So when you say 0 to 10, it means start from 0, but do not include 10. So it will go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10. And usually this is the same as, means the same as this for, which is much more common. In range 10, do something. Now we will see do something. Let's say echo, print, print I. Are we together, guys? This would be the equivalent of it. Now, notice the missing curly brace and the importance of the colon. The colon is the demarcator between the conditional and the thing to do and the presence of indentation. Right? So if I run this, there we go. I get all of these numbers. So this should look pretty easy to you. Isn't that, guys? Does that make sense? So with that there, let us do something more sort of sophisticated. Suppose I do this. I already have a bunch of numbers. So now we'll introduce arrays or lists, which are synonymous in Python. So let me just say that some counts. I'll just take counts. And then whenever you create a list or an array, which are synonymous, you start with square bracket. You see this counts? It's a square bracket. I can say 1, 2, 3, I don't know, 7, 11, 4, 9, some random number. Maybe I'll make it 12 just to show that this is not ordered, right? So this is it. These are some numbers, or maybe just call it numbers. Numbers, some nums. Suppose I want to do a thing. I want the square of all of these numbers. How would I compute the square of a number? Let us just say I can do squares. Let us say compute squares of a list of numbers. List and array, as I said, are synonymous in Python. So I could do this. I could start with an empty array, empty list, and I could do for, let's use our previous syntax, for item in or number for n in nums. In other words, in this list, do that. And you can say squares dot append n star n, or n star star 2. Right, square. So this is the notation for squaring it, right? Or you could say n star n, which is the same as n square, right? And so after you do this and you try to print the list, let's see what happens. Print squares. Let's see what happens and go down and see. Do you see that the squares have come about, guys? From here to here, you got the squares. So likewise, suppose I want to keep track of, I don't want just the squares. I want a map. It should say that this is the square of that. So what can I do now? I could say instead, I could start with a map. squares.
Just one question as a syntactical. Why are we calling it append? It's like append means somehow it's like appending to existing data, right?
Yes, so appending it to this list, squares, which you start out with an empty list and you're appending to that.
Sorry. Oh, okay, square. Okay. Oh, it's an empty list. Okay. No. I somehow confused the whole nums. Yeah, nums is different. Correct. Yeah. It's a new list. Yeah.
So suppose you want a table. Sorry. Value pair. Like a number. So in other words, you don't know 144 is the square of what? And square. So suppose you want it like this, a key value set, right? Just say value set. So then how would you do that? What you do is there is a data structure, call a map or a dictionary. Right? Let me just call it squares dictionary. People, what in C, C++, Java people call maps, hash map, etc., or hash table. In Python world, they use the word dictionary. So whenever you just assume, guys, somebody is typing furiously. Could you please mute yourself? So for number in nums, now what I would do is I would say squares and then key. What would be the key? The key is given in by this. You would say n, and you would say is equal to n star star 2, right? And now let's try to print the squares and see what happens. Oh, something print a list assignment index out of range for n in nums. Something I did wrong. N is square dictionary.
I think the n in nums is actually the value of nums, right? So that's why it's going out of bounds. I guess the squares is like so basically you have to do for the index of the list, right? So basically,
no,
I think you have to do the.
Oh yes, my fault, guys. See, what I did is I started to do maps. I should not have added to this. Yes, it's a typo. I'm trying to add to the dictionary, isn't it? This is the key and this is the value. Right? And when you do that, then, and I should not print the list, but I should print the dict.
Yeah, exactly. Yeah.
So now we can see it as a table, guys. You see 1 square is 1, 12 square is 144, 3 square is 9, 7 square is 49, 11 is 121, and so forth. Does that make sense, guys? So you got introduced to data structures, and most of the time, when you come to data science, these are the only, predominantly the data structures you'll need most of the time. You won't see you any other data. It is as simple as that. If you got these two, you're done. Right now, contrast that with things like C, C++, Java, where there's a very rich set of data structures. It turns out Python also has a collections module, a package, which has a lot of very good data structures. But most of the people, they tend, for simple uses, they don't use that. Data science people in particular don't use very often those structures. The reason being, Python is a very slow language. You don't want to iterate over or run through a long list or a dictionary. So I'll give you an example. Suppose you create a list of 1 million numbers and you want to iterate over it and find the squares of them. If you do it in Python, you'll literally be 100 or 1,000 times slower than doing it in C. So what people have done is that because machine learning or artificial intelligence, the foundation is numerical computing, and those numerical computing libraries have long ago been perfected by people, the older generation of people like me, even before me actually. So when I was in grad school, a lot of these libraries were already perfect. They were written in Fortran. So those libraries live, the BLAS, basic linear algebra system, etc., LinPack, LAPACK, Atlas, C. Those are all Fortran and C libraries. So what people have done is they have created Python bindings for it. And when you use that, then your operations are extremely fast, like lightning fast. Are we together? So maybe I could sort of illustrate that. I don't know if this illustration will work. I'm just doing it off the top. But first, let me introduce how you can do that. So when you create an array, so suppose you create an array in nums, right? One way to create some numbers. Let me just use L, simple list. Right? Simple list is simple array is equal to, we can say, range 0, let's say 0, or you can say 1 to 1 million, 1 0 0 0 0 0 0. So it's a 1 to 1 million, isn't it? Array. Let's see if this runs through, by the way. Yes. And so what is the length of this? The way you find the length of an array is, you can say simple, apply the length command. Length command can be applied to all sorts of things in Python. And when you do it, it will say there are a million items.
So see if I didn't understand the use of the constant there. Inside range, you said 1 comma, and then you had a 1 underscore something.
Oh, right. So the underscore is just for readability. Otherwise, you're busy counting zeros. So you just for readability, you put underscore and you put it in groups of 3. That is how we in the US we always go in terms of 1,000 million, billion, trillion.
So this is the equivalent of a comma in normal notation, but since comma has a special purpose.
Yes.
Okay.
Exactly. Yeah. You got it. You use underscore here. And so suppose I do something, and I hope this experiment works. Suppose I want to find the square of array. So how would you find the square of array, right? Let us say that this is, we use our typical list, what we just learned. So how would we do it by now? For n in simple array, right? For n in simple array, square of array is equal to, you would say, sorry, n star n, isn't it? Or n star 2, let us say. Let us run this and let's see how long it takes to compute it. So I'll hit enter. It took 179 milliseconds. Unfortunately, my machine is a bit of a beast, so I wish I could show it more illustratively on a slow hardware. Now, what happens in Python, for data science, especially in our field, we don't use arrays like this. We just try to avoid it because it's too slow computationally. So now what we do is, suppose I do this, NP array, there's something called NumPy, and I will import that library, import NumPy as NP. So what NumPy is, it is basically the arrays, multidimensional arrays that are actually implemented in Fortran underneath it. And nothing on earth ever beats Fortran, unless you write hand assembly code. And then also it's doubtful it will beat Fortran. But Fortran is just absolutely what you use for scientific computing. So somebody once asked, is there anybody still writing code? You'll be surprised to know that most scientific computing, especially weather simulation and complex fluid dynamics and ocean dynamics, everything, and large particle accelerator simulations, they are still all done in Fortran. So NP, that is range. Let's say.
Asif, I have a question.
Yeah. One second. Let me finish this, then I'll take that. Go ahead.
As if you mentioned that you're multiplying the arrays, right? So for that square of arrays, are we not supposed to do an square of arrays dot append and
Yeah.
then a square?
Yeah. Oh, okay. This didn't work. I apologize. Square of arrays, dot append. It should be. I take this back. That's why I was wondering. Yes, this is the right way. This is probably what you were asking.
Yes, that's correct.
That is. Thanks for catching that. So here we go. We created a NumPy array, and now what I'm going to do is, suppose I want to find the square of it. You know how would you do the NP square? NP array. That's it, right? And now, do you see the runtime of this? 14 milliseconds versus 216 milliseconds. Do you see the difference, guys?
Yes.
Yeah. It's significantly faster, and I could do more experiments. Like you could take, let's say that suppose you have to multiply an array by each element by some random number or something like that. Suppose you do that. So I'll show you this experiment again. It's worth doing to bring out the data science perspective of it. So suppose I take another array. Another array is equal to like at this moment, I would say random dot. So I'll have to import random, sorry. Goodness, I can't see my keyboard, and import random. And I believe I should remember that random dot normal 0.
Just one thought, Asif, perhaps in this case, like the since the data set is trivial, all zeros in a simple array, maybe the Python interpreter did some optimization. It could be in reality even worse, probably.
The array is not 0. The array is not 0. So let me see that. I created an array. So yeah. You have an array from 1 to this. This is not 0. Let me print the first few elements. And so that brings up the question.
The simple array is 0, right? Asif, I was talking about the previous one. Sorry, I didn't like bring context. A simple array is all zeros, right? I thought.
Oh no.
A simple array.
No, let's look at that. So suppose I do the simple array. Right? Let's print out the first few elements. I would do, let's say up to 10 elements, see what happens. Range. It gives you a range of numbers from 0 to 10. Do you see that?
Yeah.
That is
it. It's basically then, when you say simple array, it'll actually initialize to 0, 1 like that, each element. That's what it does.
Exactly.
Range when you put array.
That's right. In fact,
it's not all zeros. Okay.
It's not all zeros. So that's that. So now something interesting has no normal. So now the thing is, this is where, because I don't use the normal Python all that much, I myself tend to forget the syntax. So let us go and find normal Python, normal distribution, random. NumPy, no, that is normal. How do you do it in plain Python? No, this is NumPy's random. Random.normal, no, okay. Python itself. All right, let me just say Python random numbers. Let us just use that. The thing is, numbers in Python. So basic thing, numbers in Python. So this is it. You get so used to generating, working with scientific libraries. Gradually, you begin to, as I said, right? You don't remember. Oh, I apologize. This is late. Where am I? So let me just say random.random. Random. So you generate 1,000 random numbers. Let's see, 1,000,000 random numbers. Will this succeed? takes no argument. 1000. Yeah. So 1 times this. So here we go. We have created about 1,000 random numbers, another array. And now I'm going to multiply the two elements of the array. So imagine that you do dot product. Means you do a pairwise multiplication, i.e. a pairwise, element-wise multiplication, element-wise pair multiplication. So how would you do that? You would say that for, let's say, number in the one array, X, Y, but now you need to travel through both of the arrays at the same time. If you're going to multiply a number from here with a number from here, do you realize that we have to index it in such a way that we go together? Right, guys? So we can do it like this. For I, a traditional way would be I in range 1, 0, 0. Or you can just do length of it, length of up to the length of simple array, square of array, okay, of square, no, array, simple array. For up to this length, what will you do? You will say, you will create another thing. Let's say that a result, a last array, which will be the pairwise dot product of these two. So you would say a result dot append. What would you do? You would say simple array I star the other one, another array, and I. Does this make sense, guys? And this,
yes,
yeah, this will produce your array. Let's see how fast this can run, and we'll see. Oh, what did I? Oh, sorry, equal to sign I missed here. And what did I miss once again? Simple array for I in length. Int object is not iterable. Oh, actually, let me just say in not length. Sorry. It should be range, length, etc., etc. Let's just say for I in range, okay. We already know what the range is. I'll just put the range explicitly here. That was my mistake. It is indeed true. The value is not iterable. Okay, so let's do that. And now why are we unhappy? Float object in range, append. Result.append, simple I, okay, is not, float object is not scriptable. So here there is a subtlety that came in. The simple array is actually something called, and I should introduce that, it is something called generator. So you can't actually do this with a generator. So the simple array, I'll just write one more thing here, and you'll see why I do this. Simple array is equal to I for I in range 1 underscore. Yeah, this is a very cryptic syntax. Just take it as a fact for the time being. And result is simple array I times another array I. A float object is not scriptable. Why did I become float? Oh, for I in range. Okay, this is a very simple thing. Int. Now result I. Okay, guys, help me identify. Let's take this as an exercise. What could I have been doing wrong here? This illustrates that if you don't do something for a while, then it begins to break off. You do a lot of data science and you begin to forget the basic simple thing. Let me print this array. A few elements of the array, 0 to 10. Yeah, so this came through properly. So for I in now. So now I don't need to do this. I can do this in range. Okay, so yes, I don't need to do this. Simple array, and result is equal to result.append simple array, another array. So the problem is in the another array because it is another array I. Another.
Can you look at the data type of that?
No. The reason is that this happens to be, this was the problem here. See, you can't iterate over it because it's just a random number. It is one number. So I have to do for I in, and I'll explain what this syntax is. I random for I in range. This is the funny syntax I wanted to explain, but let me use it before I explain. Yes, now it will go through. Everything will go through. So that was it. The rest of the code was fine. Yeah. So so at this moment, let me make the point I'm making. But assume that this produces an array of random numbers. Do you see an array of random numbers? A million random numbers printed out the first 10. Let me comment this. Produce an array. So this was it. Actually, I really think I'm using the Python's native random after a very, very long time, almost years. Generate a lot of random numbers in Python, plain Python, not use one of the libraries. So this is what this does. And simple array is just a bunch of numbers here. Actually, I didn't need to do any of this. I in range would have been just fine. But here we go. We are multiplying these two. And it took 129 milliseconds to do. Now, see what happens if I do a similar bit of code using NumPy. So suppose you have a NumPy array. So let me just take the array to be X. Right? X is equal to np dot a range, pretty much the same thing I'll do. A range 0 to 1, 1, 0, 0, 0, 0, 0, 1. Right? You have an array of this. I will also generate a y. Now this time I'll use numpy.random. Import np numpy dot random, right? That's random. And now if you do is equal to random dot normal. I'll just take I could have done random or 1, and I'll take a number 1 underscore 0, 0, 0, 0. So many values. Now see how fast it goes. And this is the point. Suppose I want to do a dot product. First of all, look at the simplicity of the syntax, X star Y. Right? I'm sorry. One has a shape greater than 1, NP array shape 0, 0, 0. Let me look at my keyboard. Then we have notice. So guys, notice the difference. Here, you see this syntax. We are multiplying these two arrays. It takes 129 milliseconds. And this takes 11 milliseconds. Right? And it gets much worse if I add a few. Let's make it a billion. Oh, goodness. Give me a moment. 0. And suppose I do it for a billion lines. And obviously, I need to make sure that this another array also is a billion. I need to run that also. Right? And first of all, notice how long it takes for it to generate a billion items. Execution queued. And even here, it is taking a very long time to just produce so many numbers. Do we see that, guys? In fact, I don't think simple Python will survive this. It might not. Restart the kernel.
Oh, it may just.
It may just crash. This is it. The Python, remember, is a scripting language. It's not really meant for heavy duty stuff, the plain Python. So when you, in machine learning, when you think you're writing code in Python, you're not really writing code in Python. You're writing code actually in Fortran and C, but it looks as though you're writing code in Python. Right? So let me run this now. Oh goodness, I don't think this will even finish, right? So let's not try to even make it finish, but it sort of illustrates the point. But now I've used some peculiar syntax. Restart. I've used some peculiar syntax and I'll explain it. First thing you notice, guys, that before I go into it, assume that these two arrays exist. Simple array and another array exist. Would you agree that this is much more harder to understand than this, just X star Y?
Yes.
Yep.
Isn't it? And this is the point. In data science, we use the NumPy library, which is basically Fortran library under the covers. And this supports, Fortran has one beautiful thing. It stands for formula translation. And quite literally, the way you write it in mathematics on a piece of paper, your code will look very close to this, right? And that is a huge positive. Besides the fact that it runs much, much faster in NumPy than it runs in Python. Normal Python pretty much bails out on you after a little while. So in fact, it's a long time that I ever did these things in normal Python, which is why you see me trying to recollect things, fumble around. Go ahead.
Do you have destructuring concepts in Python? Like, say, if you have a long array and you want to automatically assign certain values to variables, like in JavaScript, there's a concept called destructuring. Is that there in Python? I'm just curious.
Give an example. So suppose you want to create an array and you want to fill all of it with 2.
Okay, so let's take an example. Say an array has 3 elements, say 1, 2, 3. And then I say A comma B is equal to that array, correct? Automatically in JavaScript, A is equal to 1 and B is equal to 2. The first 2 elements get assigned. So I don't have to define those values. They automatically, in any other language, I have to say int A and then assign them.
We have it, yes. Python has that, same convenience, slightly different syntax, and you'll come to it.
Okay.
It is very elegant, actually, that the return values of this thing. So what you're talking about, so it's a little bit of a digression, but I'll say that. So suppose you want to say, suppose you want to do like this. A, B, C is equal to 2, 3, right? This will work just fine, right? And these things work. They take the right placeholders, but there's more to it. I know what you're coming to. We'll come to it gradually. But at this moment, let's pay attention to it. So the first thing we realize is NumPy is far more simple syntax than the normal Python, which is why I said the only Python we need is a basic amount of Python, because we'll be using data science. AI is all about NumPy and PyTorch and TensorFlow and scikit-learn. It's not so much about the vanilla data structures in Python. You know your for loops, your whiles, etc., and basic functions and a bit of classes, and you're done. Right. So now I'm going to teach you something about what is called list comprehension. List comprehension. I have used it above. You didn't realize it, but I will now do it in a more structured way. So suppose you have a list. So let's take a list. X is equal to Once again, I will take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose I have a list like that. And suppose you want to take a condition, you want to create another list, Y, which is made up of, suppose the problem is create a list Y, which is made of the square roots of X. So how would you do that? A traditional way you could say is that Y is equal to this, right? And then you would say for num in X, right? SQRT, right? X num root is equal to, now you take the square root, right? So if you're doing numpy, it would be, so let's import numpy here somewhere, which is bad practice. You should put your imports at the top, but we'll do it here as np. And you go here, and again, let me center it, npy.sqrt x, right? And you can say y.append num root. This goes through. So there you are. What have you done? You have created, and let's print out a few elements. Why not print y out? It should be easy. So you can see that y is made up of the square roots of these numbers, isn't it? Y.append and so forth. Right? Now, this is, oh, sorry, what I did was silly. Num root for num, not that, I apologize. So now you have 10 square root. I was wondering, how did I get that? So many. So far, so good, guys. We agree that the square root of 2 is 1.4, 3 is 1.7, 4 is 2, and so forth, right? So we do it like this. Now, still within normal Python, there is one more syntax, which is more elegant than this. It is called list comprehension. List comprehension. And this is something I find very elegant in Python. I like in Java, I really miss that they don't have it in C++, C, Java. They're trying to have it, but so far I think they don't have it. What I can do is I can say num star star sqnp dot sqrt num for num in X. See, what am I doing? I'm going to iterate over every element of X anyway. Did you see this for num in X? But I can write it right here, and I can say for every number, return me, this is the return value, return me the square root of num. And now what happens is, you will notice that this produces for you the same result. Do you see this, guys? Now, you would agree that this is, once you get used to it, this is a bit more elegant than this. Would you say that?
Yes, Asif.
Definitely super elegant, actually, yeah.
So Asif, you're running for that list, it's basically returning a method, correct? So you're calling a method for the right-hand side.
Yeah, no, what it is saying is that for every number in X, take the square and that's the return value. So you collect that into a new list. Okay. So it's a mapping from a list to a list. If you think functional programming, right, list comprehension is pretty much a mapping from one list to another. You just tell which function you're applying to that, each element of the list.
Okay.
So numpy square root is the function you're applying to that.
It will work as long as there's a one-to-one mapping, I guess, right? So it's a one-to-one. If there is a one-to-one, that's the only case it will work.
No, so that is another beautiful thing. It doesn't have to be. So let me show you what if I want to take it only for even numbers. So suppose I say z is equal to list comprehension np.sqrt num, right, for num in X if num is equal to.
Interesting. So basically, it's at the back. It's creating a dynamic. It's actually a dynamic array like Java, like probably like a correct. It's the dynamic. The list is dynamic data structure.
Right. So now you see, right? Now what's it doing? It is computing the square root only if it is an even number. Right?
Interesting.
Yeah. So you can do pretty amazing things in Python just by using list comprehension.
So Asif, here you're using dot square root of num. Say, suppose I have an independent method, I can call that method and provide num to it, and that would return that particular result.
Let's do that. Huh? Let us define. I didn't teach you functions, but let us jump ahead and define a function. Yeah. Function. I will do. Let's just say translate. I'll just put create a function for that. Let us say that you give it a variable n, and it returns, just for the fun of it, n plus.
Before we go into the function, just on the list comprehension statement,
Yeah.
like if num modulo 2 equal to 0, right?
Yeah.
That has to be a single statement, right? There can't be, if you want to have one more condition, that can't happen.
No, you can. If num is equal to 2 and num is not equal to, and num not equal to 4, let us say, right? So now let's do that. You notice that now you get only 4 numbers because 4 has been avoided.
Okay.
2,
so you can have
10.
a complex Boolean condition there.
Yes, you can be pretty sophisticated there.
Okay.
It's amazing, isn't it? It's very nice, actually. This is one of the things that makes you like the differentness of this. Now, suppose define a function. By the way, I've explained function, but I hope it's simple enough to understand what it is doing. Given a number, it will return the number plus 3, right? So suppose we run this, and now we do another one. Now let's try to do a list comprehension. W is equal to translate n for n in x, right? W. Does it do that? Take all the numbers and add 3 to it?
Very nice.
Any function that you want. Right?
Very nice.
Called list comprehension. And I would strongly suggest that when you're using plain Python, extensively use list translation. So what will happen is when you come from some other language, you will tend to use a lot of the traditional for loops, etc., when you're dealing with arrays or with lists. But there's no reason to. The moment you see a list, ask yourself, can I write a more elegant syntax just using list comprehension? Right? And so this is it. Now comes a thing about NumPy. How would you have done this in NumPy? NumPy would have been y. Let me just use a y NumPy is equal to np sqrtx. This looks the NumPy version of it. What do you notice? Now, how many of you are impressed that you can do it like that? You don't have to do even list comprehension. So this is called NumPy broadcast. The operation is automatically broadcast. The concept in broadcast. So this is a NumPy, or the data science specific construct. We treat lists as vectors. So in mathematics, we can take the square root of vector, and it would be the square root of every component of that vector. NumPy will respect that. Do you see that, guys? Is this simple to understand?
Can you repeat broadcasting again, please?
See, what is X? Just to remind you, what is X?
It's an array of numbers.
It's an array of numbers. So let me just print it out, X. Right.
See, so, specifically here, X is an array of integers, and
yeah.
Y NumPy would be an array of floats.
Yeah, and it doesn't matter. It doesn't matter. It will auto-convert it to, yes, this is it. Here it is. So X was this, and what is Y? It is this.
So Asif, you do not have to traverse the entire array. What you're saying is automatically did the square root of those numbers and provided a new array.
Yes. So it will do to every element, it will apply that function.
Yeah, this is fabulous. Really, really fabulous.
Yes, and that is the power of the AI libraries in this, and which is why I told you guys, right, that it is good to know Python, enough Python, but you don't have to go overboard in Python, because the machine learning libraries that we use are very specific to machine learning, and they are just amazing.
So Asif, now a curiosity question. So you put y numpy equal to np square root of x.
Yeah.
Let's say you had an arithmetic term after that, plus another array operator, and the cardinality of that array is not the same as this array.
So let us add three to these numbers, huh? All of them, or 300, so that it becomes obvious. Even this will get broadcast. Any operation you do will automatically happen to every element of it. Do you notice that the result is every element now starts with 300 plus something?
And if that's another array whose cardinality is not the same as the cardinality of x, then what happens?
Right. So the overall array will return the cardinality of x, which is 10, the result array. And so to every element, you're first taking the square root and then adding 300.
Now, if instead of 300, if I had another, let's say it's np square root of y, and the cardinality of y was slightly different from x.
Yeah. So let me just say a power x 4, the fourth power of x, let's say, right? So now let's see what happens. Sorry, you can't do np power, the syntax is wrong. What did I do? Has no attribute called power, exp. Okay, let me just do exp. That would be, why am I having this issue? Exponent is there. Return array must be of array type. Yeah. So this is, first let us see what type it is. So yeah, we have to go a little bit slow. Let us go a bit slow, print it out and see what comes out. Print this. It is not letting us do np to the power 4. Okay, let me do it the other simple way. You have x. See, the moment you have, because x is not a numpy array. Did I not make it a numpy array? Yes. So one of the things you have to remember is that when you deal with numpy, try to only deal with numpys. Like start with an array that is inherently numpy. So let's redo xx is equal to np that array of x, and then print x, and then first do this thing, and then I'll show you what we mean by that. Right. So you see that, and now let's try to do zz is equal to np dot exp. Let us say we take xx3, right? And then we do print 3, print zz. Let's see what comes out. Something it didn't like. A broadcast, see, it's making a broadcast complaint. Return array must be of type. Arrays must be of type this. So it is array. Yeah, maybe it doesn't like that. Okay, I'll just do, just to illustrate the point you're making, I'll come and figure it out. Let's take the third power of it directly. So now you have two arrays, both of them with 10 numbers. And your point was that, can I apply broadcast to the first one, right? This will lead to a broadcast value, the squaring of each number. And can I therefore add either ZZ or directly XX star star 3, right? And this will go through just fine. Premji, that's what you were asking?
One second. So I was actually trying to see if the cardinality also will match. So in this case, the cardinality is the same.
Yeah.
So let's say X has cardinality of, in this case, what, 10, right? Let's say we had another array Y, which was cardinality of 7.
Then it will fail. So I'll tell you that. So Y is equal to NP dot array. Let us say this. Let us just take something 2, 4, 3. 2, 4, 5. Now the sizes are different, isn't it? And now see what happens when you try to do this.
If you dot array, I see you have a comma there instead of dot.
Oh my goodness, yeah. This is it. So when you look at this, what is it complaining? Broadcast, remember? And it will give you the message, value error. Operands could not be broadcast together because their shapes are different. One is 10, the other is 3.
Okay.
Right? So it will give you those error messages. So the big lesson to learn here, guys, is that we should use NumPy as much as possible. So take it as a exercise that today you will go and get introduced to NumPy. NumPy is just magical. And most of it is, if you remember your high school algebra, you know NumPy. So NumPy API. Suppose you go to the API doc of NumPy reference. What you will notice is that you almost don't have to learn anything. Let's go to numpy.org, docs, manual, etc. Arrays. So how do you deal with n-dimensional arrays, etc., etc.? Broadcasting is something worthwhile learning. Actually, let's look at the API. NumPy, py, then PyDoc. The guide NumPy, doc strings and NumPy doc strings guide doc for C. Now don't learn from this. Let us go to some basic NumPy tutorial. NumPy API doc, right? And NumPy documentation. Let's start from here. So here it is. You can read the documentation on the web, right? And you can see the API reference. So do the quick start tutorial. You'll be absolutely surprised how easy it is to pick it up. Once you have installed NumPy, you play around with the arrays, but you have to become familiar with it. See, it is easy, but it doesn't mean that it won't take time. It will eat up the better part of your day to understand this, do all these very basic operations, adding arrays, multiplying arrays, and things like that. And I would like to say that today, just give to that before. Next time we'll do functions and other things. But see, more than anything else, the heart of machine learning, right, is arrays, multidimensional arrays. So you have to know NumPy, and in PyTorch, you have to know tensors. If you know these two things very well, you will realize that other things come very intuitively. And NumPy is as close to just writing mathematics on paper as you could be. It is, once you get used to the syntax, right, it's very, very, very intuitive. So how do you learn the basics? So I would say that give today, tomorrow to picking up the basics of NumPy.
Asif, am I right to assume that NumPy, although we keep referring to it only in the context of arrays, it can also do all the matrix calculations, right?
Yes, multidimensional arrays. Absolutely, absolutely, it can do that. All of that.
Whoa,
it's very, very powerful. NumPy, was it is what took. It just made it easy to use 30, 40 years of scientific computing and all the wealth of information that had accumulated. See, guys, when you write software, business software, right, that comes and goes. Right? Today it's one language, tomorrow it's another. Today it's Angular, tomorrow it will be, something else, maybe React, right? And it will keep on moving forward. J2E came and the EJBs came and EJBs went. DOM. Some of you may remember COM, DCOM, and whatnot, and MFC. All of these things come and go. They're transient things. But mathematics is more or less eternal. And the numerical libraries that people write, it takes many, many years to make them A, fast, and B, correct. Right? And it shows up in many ways, actually. So for example, if you want to take the average of two numbers, intuitively you would write in your code A plus B divided by 2, isn't it? But actually that is wrong from a numerical perspective, because it will lead to overflow. If both these numbers are too big and they're close to the maximum value that that data type supports, A plus B will already be an overflow, and divide by 2 will return you a random number. Right? So you have to know that to take the average, you have to first take the difference. You have to do the smaller of A and B, whichever it is. Let's say A is smaller, A plus B minus A over 2. Right? You have to do it like that. And it takes a while actually to go fix bugs. Sometimes these subtle bugs, and this bug is very interesting. It turns out that in Java's sorting algorithm, they had to find the median somehow, or the middle guy at one point. And for almost 10 years, this bug stayed in Java sorting algorithm. And Java sorting algorithm is written by people who are an army of PhDs and some of the most rigorous people in the world. Right? So that is the nature of scientific computing, that when you do deep down algorithmic stuff, it takes many years to make it perfect. So those libraries, BLAS and LINPACK, LAPACK, ATLAS, they have been perfected over decades. And secondly, their performance is absolutely close to the bare metal performance you can ever get. Nothing comes close. So people don't try to reinvent the wheel. It's taken a long, long time to build that wheel. What they do is they put layers, usability layers. Think of it as user interfaces on top of it. And Python, in some sense, is a very simple user interface, because the only sort of people who were using Fortran, and see, people like me, who are deeply into scientific computing. And it's not sort of democratized. Most people don't learn Fortran. In fact, they believe Fortran is dead. Most people don't want to learn C these days. They start with Python, right? And they don't want to learn any other language. Maybe they'll learn Python and JavaScript, and that is it, right? Or Java or something like that. So how do you take all that intellectual heritage and make it available? That is what NumPy, like SciPy does. SciPy is impact.
So Asif, in Python, it's an interpreted language, right? So basically, for the libraries, are the executables already available when the interpretation happens?
Yes, actually, when you install this thing, Python's machine learning libraries, right? When you do conda install NumPy, you'll actually see that it is installing Fortran. And if you look at the messages when it does the installation, you will suddenly realize that it's installing Fortran. And so a call, when you make an interpreted call, A star B, right, X star Y, right? Let's go back to our code. When you do something like, where is it? Something elegant, like, I don't know, where did I use this? Let's say the last statement, right? So this is deliberately a mistake. So let me just say broadcast mistake. Mistake to show. So forget this. Look at this part. Look at this part, right? When you do something like that, the array that you create, like for example, this array that you create, it is not in Python memory. This array is actually sitting in the Fortran and C memory.
Ah.
Yeah, that is it. And so when you multiply, all it does is that it calls the C binding and says go multiply it by 3. Third power of the array.
Interesting. Ah, very interesting. So basically, it's literally that C Fortran, that library is pre-compiled to that platform and made available as a library. Everything is there.
Absolutely. It is it.
Oh, and then you use that super fast malloc and all the super efficient routines, I guess, like under the hood.
In fact, because it's Fortran-like, a lot of these things are in Fortran, so there's not there is no pointers. It's extremely fast. It is what today we call cache conscious algorithm, right? The beauty of that is data will be highly contiguous. They will load in memory, in not just the memory, they will load into the CPU cache. And quite often the computations can be done in the L1 and L2 cache itself. You don't even have to go to the L3 cache. So you can imagine how billions, like literally millions of times faster the entire thing becomes.
So
I mean, it's exploiting the locality of reference property, right? The array is contiguous, it's just exploiting that property. Yeah, I mean, very nicely. Yeah.
Asif,
Mhm.
do you have for each loops in Python? You know what I'm saying, right?
No,
Elements.
the JavaScript for each syntax is not.
Okay.
See, list comprehension is your for each.
Okay. Okay.
So there is also something called a generator, which does a lazy evaluation. So let me explain that. So for example, if you do this, let me call W lazy. And instead of square brackets, if you do translate N for N in X, right? And so let me put it here, print W. So you can see that with list comprehension here, with list comprehension, you get eagle evaluation. Eagle evaluation is a fancy word of saying you get exactly what happens is exactly what you think happens. Namely, all the values of W array are computed. But when you do, with these things are called funny things. These are called, with generators, it is lazy evaluation. Now, why would that be useful? Let's see, print W lazy and see. See, when you notice that I printed W, it actually produced the numbers. But if I just change the square bracket to curvy bracket, and I try to print W lazy, it doesn't do that. It actually gives me a generator. Generator says I'll evaluate it if you ask me to evaluate it. So if you iterate over me, then I will do that. So suppose you say for
Wow.
W lazy. So the reason is it gives you optimization, because if you can give a formula and you can say, suppose you want to do it only for first 10 elements or something like that. Then you don't want to compute the entire thing. But if you do that, it will still produce the same result, right? Because then it will lazily evaluate it. Right? But the beauty of this is, suppose you do this. Why is this elegant? Suppose you did this for I in range 3. So let's say that, imagine that 3 is a huge number. Huh? So suppose that you do a print num. Then what happens is the rest of the translations are not even printed. So print only, compute only on demand, right? And so what happens is here, these three, what did I do? Print for I in number, so hang on, W. So I don't think you can index into W, but we'll try it. I think this will throw up. For I in W, I think it will throw up. No, it did, it computed it. So what happens is when you ask for 3 elements, it will only compute the 3 elements. So what's the advantage of this? Can you identify the advantage of using generators? Guys?
If the function takes a lot of time, you save it.
Yes. So those values that you don't refer are never computed, and that's a massive saving. So generators, I would say, is one thing that I find most Python programmers don't use. But you should ask yourself, is a generator a better thing to use here? It's one of the best practices that more people should adopt, using generators.
So Asif, in JavaScript, there is a concept called generator functions too. But in that case, the generator function can return multiple values. And you first get the first value, you say next, and then gives you the next value. It commutes the next part of that method and then goes on like that. I don't think they mean the same here, but yeah.
Here it is an iter. You can do that. You have to put an iterator over it. The moment you put an iterator over generator, you get exactly the same effect.
Okay. I think they're trying to create, in that case, I understand why they did it in JavaScript. I think they are trying to create like a thread concept in JavaScript. So if you have a thread concept, you fork few threads and you want to get it information from there and then move on, and then generator functions is useful.
Yeah, maybe. Yes. I don't know the threading, the underlying architecture of JavaScript. I just know JavaScript as a language, and on the surface, the syntax of it. But its underlying things I don't understand. So I can't comment on that.
Okay, thank you.
Asif sir, sorry, go on.
Go ahead. Go ahead.
Thank you. So what is the keywords or something that is showing that it is a generator? Like, can you explain the syntax there?
Yeah, this is it. When you print it out, do you see it says that it's a generator object? Try when you print WLazy, you don't get anything. You just get the word generator object.
So WLazy is a variable, right?
WLazy is a variable, and that points to a generator.
I think Asif, Harini's question is around the square brackets versus the curved brackets.
Yes.
The square bracket is generated an array. In the other one, it is a generator.
Yeah. So if you use this curvy bracket, Harini, you are saying make it into lazy evaluation mode. In other words, produce a generator.
Oh.
That is it. That's the only difference. And it's quite elegant, actually, how much performance sometimes you can gain simply by making this little change. Go from square bracket to, in list comprehension, to a curvy bracket while doing comprehension, and you end up with a generator.
Thank you.
Quick question on, if you have multiple cores on your computer, how do you make something like NumPy use multiple cores? What I see here is every time it executes, it only uses one CPU.
Oh, how do you do parallel computing with this? There are ways of doing that. Let's not get into that. But the simple answer is yes. So first of all, right, NumPy is lightning. When you look at libraries like NumPy, under the covers, they are very smart. You don't know how it is doing it. It's doing it in a very smart way under the covers. And there are ways to give it very explicit hints.
That's wondering, it's something that we will just add as a declarative somewhere, and then it starts using
exactly. At the beginning of your code, you just declare this, and then that is picked up.
Okay.
And so there's a lot here. Then Dask and other things. So we'll come to that. See, here's the thing. Let's begin to learn to walk before we run. But we'll come to that. All of those lovely things are there. See, scientific computing libraries are just amazing. Pick up enough Python that you can enter into the scientific computing libraries. And after that, the AI libraries. And AI libraries are like absolutely the way next level compared to normal Python. Because they are leveraging not the syntax of Python so much, they are leveraging the underlying Fortran and C, which are absolutely as fast as it can be. You're leveraging 30, 40 years of work there, 40, 50 years of work.
But as just trying to connect the dots, I was wondering, like, that's more of a distributed system design problem, right? Like, the problem exists whether you like do NumPy or standard Python, right? That like basically that CPU, that process CPU code still exists. Like that problem still will exist, right? I thought it's independent of, or is there something?
No, it goes basic, more basic. You do it in Python, it's an interpreted language. Every line of code is converted to machine code on the fly when you run it. Any interpreted language will be gazillions of times slower, I mean, in a very colloquial way speaking, than fully optimized binaries like that produced by optimized Fortran or optimized C.
Oh no, that I absolutely. What I was thinking was like the problem of like single versus multiple core. That problem will exist in both the scenarios, whether you use standard Python libraries or use NumPy. That's a different problem to solve, correct?
That is a different problem to solve. But having said that, you have to give the hints to the NumPy that you have the access to all of that, and it will use it.
Okay. Which core and core affinity? I guess like core affinity and all those. That's what you're talking about, right?
Yeah.
Like all those smart.
Yeah, you can do that. You specify the number of, you don't even have to give affinity to a specific cores, but just declare that these are the cores and you run with it. And see, what happens is that we are talking of NumPy. Fact of the matter is, NumPy with all its power has one tremendous limitation. It runs in CPU memory. CPU is a general purpose thing. It wasn't designed for floating point operation. The other thing is NumPy's basic unit float is a 64 byte float, right?
Okay.
Machine learning and gradient descent, actually, you don't want that high degree of precision. You want to actually use 16 byte precision, very low precision floating point operations, because your numbers are between 0 and 1, you're doing gradient descent. 32 is the standard. 16 sometimes gives you amazing results without loss of accuracy, and it runs almost 10 times faster. So what happens is that you want to run it, first of all, on actual tensor, dedicated tensor processing units. So when you, NVIDIA's card and Google's TPU in the cloud, they have dedicated tensor operators. They are meant for matrix multiplication and differentiation. Literally, imagine, see, Intel is written on the Intel 32 instruction set, right? IA32 instruction set. Isn't it? And now they have expanded it to AMD 64 and all of that. But imagine an instruction set that is designed from the ground up to only do matrix multiplication and differentiation. That is it. A very tight instruction set designed at that level. So you can imagine how blazingly fast it will be. That is why there was maybe I show you a demo. It's an old demo that NVIDIA did as a marketing stunt, but it sort of proves the point. I'm not being a shell or a mouthpiece of NVIDIA, because this is generally true of all tensor processing units. It's an old demo they did once, NVIDIA Mona Lisa demo. Okay, so guys, I hope you can hear my sound. I'll make sure that you can. Share computer sound. Just watch this for a moment. Demo GPU.
We can't hear the sound.
Yeah, we can't, nor can I. So let me go to the one where the sound is more clear. We'll do this one. No, oh, sorry.
Oh, Leonardo. And he's going to paint a picture for you guys.
Actually, let me start from the beginning.
All right, I introduced to you Leonardo. And he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully.
So guys, before I do that, you see that this entire system is a giant array, right? Two-dimensional array, matrix system. Right?
Yep.
So the matrix multiplication means all elements act at the same time. And see what happens when compared to the CPU when this is done.
When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration. In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So I hope, guys, you with this video, you see
7.
You see why you should use the scientific computing libraries, right? NumPy is this: when you're running on, when you use PyTorch, right, the tensors, and you use TPUs, your performance is this. So if you guys have a laptop that doesn't have a discrete graphic card with a CUDA support, you are doing it like the first Intel CPU, sequential computing. Whereas when you do it with this PyTorch, you see what happens. That you're just looking at a dimensionally more powerful machine. Right? And that is what is used for AI these days. Make sense, guys?
Yep.
That is it. And so today we have been 1.5 hours. I'll stop here, guys. So what is the homework for this? Go learn NumPy. It's very easy. It is as close to mathematics, plain mathematics as it could be. And you would love it. Yeah. It's a large library. You don't have to start with everything. Start with the basics, right? The beginner's tutorial, the quick start tutorial, beginner's tutorial. There are many tutorials here. And gradually you'll realize that you can't think of a library or an API design more simply for mathematics, for basic arithmetic, right? All right, guys. And so with those, I'll stop.